All right, we are off. Well, we are going to discuss part 4, which is basically biological chemical processes, soils, and animals and their relationships to plants. I'll level with you. Soils are not as exciting as they sound. They're a little dull, but they are a very important part of geography, so we will have to talk about them a little bit. So let us start with Unit 20, biochemical cycles. And in this particular picture, we can see sand dunes in the Tibetan Plateau. And this picture is interesting because it kind of shows what the lithosphere is like, the outermost layer of rock, where you have vegetation in the green areas and where it's completely exposed and unbound and just blowing around in the wind, as you see in the sandy parts. So the lithosphere, again, is the outermost layer of the Earth's crust, which includes bedrock and soil, and a lot of what we discuss will be about the lithosphere. Pedology is the study of soils, so you'll hear the phrase pedology or pedon occasionally in this lecture, and pedon is Greek for ground. We'll also talk about biogeography, which is the study of plants and animals, the biology and geography. And we'll talk about biogeography, and it's divided into two main branches, plants and flora, which is phytogeography, and zoogeography, which is about animals and fauna. Fauna is a fancy name for animals. So the building blocks of life is carbon, hydrogen, and oxygen, and also trace amounts of nitrogen. In this picture here, this is Washington State. This is a big evergreen forest. Evergreen forests consume and hold in a lot of carbon, as a lot of forests do. So they're described as carbon sinks. The biggest carbon sink is probably the Earth's crust itself and the ocean. But living organisms are made up of organic compounds, specifically carbon, hydrogen, oxygen, and nitrogen. And those chemical compounds, especially carbon, are the building blocks of life on Earth. If you've ever seen Star Trek, occasionally you'll hear someone say a carbon-based life form. And that's basically when they come across something similar to life as we know it, it's described as a carbon-based life form. So here's an example of leaf litter on the forest floor in, I believe, Minnesota. Leaf litter comes down in the form of leaves that drop, and then these leaves break down and get into the soil and improve the nutrients of the soil where there are forests. And they can also change the component of the soil too. Soil can change over time with weathering and moisture and heat and the breaking down of plant material and so on. So it can form a thick, rich layer on top of the soil called the humus. So this is an example of forests, probably in the late fall in Minnesota, with leaf litter on the ground before it breaks down. So there are some important cycles in nature, the carbon cycle and nitrogen cycle. The carbon cycle is when carbon, the element carbon, is transferred and moved around within the earth. A cycle is something where something continuously moves. Energy from the sun is not considered a cycle because it doesn't go back to the sun, but the nitrogen cycle and carbon cycle are these elements are continuously moved within our atmosphere and our environment. In this particular picture, it shows petagrams of carbon, and that's basically a large amount of carbon. And the arrows show how much of this, a petagram was 1 billion metric tons, how much of it moves from one place to another within a given year. So the atmosphere has 830 petagrams of carbon that it gets from various sources like volcanoes, deforestation, and also carbon is absorbed into the earth in the form of photosynthesis, where trees suck carbon out of the air and then encase it within the soil and elsewhere. So carbon continuously moves throughout the earth. It can be in a solid form. Diamonds are a form of carbon. It can be in liquid form, such as fossil fuels like oil, that's a type of carbon, or it can be in the form of carbon dioxide in the air. So it can take on different forms, but it's what all life on Earth is based off of. This is the nitrogen cycle in the soil. Nitrogen is the most common element in our atmosphere, and it often will come down in the form of leaf litter. Then those leaves are broken down, and then the broken down organic matter is broken up by worms or microbes in the soil, and it's converted into ammonia, or it's fixated onto the roots of the plants where it's absorbed and then later on eaten by animals. So this is an example of how nitrogen is continuously moved in various forms throughout the earth, and especially in the lithosphere and basically in soil. So nitrogen in the air is also moved around in different phases. It can be both natural and man-made. Nitrogen is absorbed out of the air in the form of vegetation and photosynthesis. It's also released into the air from coal-fired power plants. They often will release some nitrogen and also carbon dioxide in the air. And nitrogen fertilizer also takes nitrogen from the air to make very dense fertilizer. A natural way of improving the soil that we farm in is by planting legumes. Those are beans, soybeans, chickpeas, alfalfa, clover, and peanuts. They naturally add nitrogen to the soil and improve the quality of soil. Recently, in the last 100 to 150 years, artificial fertilizers have been added to farms to increase output in the form of guano, which is bird or bat poo. That actually is a very important fertilizer. And more recently, artificial synthetic fertilizers based on nitrogen, where they push large amounts of nitrogen into the soil to improve productivity. Unfortunately, that can cause runoff, where excess soil is washed into creeks and rivers, and it can cause problems where the nitrogen sucks up oxygen from the water, and it can cause biological dead zones. This picture here is a biological dead zone caused partly by excess fertilizer rushing out the Mississippi River into the Gulf of Mexico, where the fertilizer then creates algae blooms that use the nitrogen to grow algae. But then that algae sucks oxygen out of the water, and it can create large biological dead zones where animals such as fish and others that are in these large algae blooms run out of oxygen and they can die, and you can have large die-offs. So 2013 was a bad year, and 2021 also was a bad year for a large algae bloom caused by excess fertilizer in the Gulf. Something similar happens for the same reason in the Great Lakes from time to time. Lake Erie is the furthest south and the shallowest of all the Great Lakes, so it's the warmest. And a lot of fertilizer from various Midwestern farms can run off into Lake Erie, and that also can create algae blooms that suck up oxygen and can kill off fish in large parts. So the western part of Lake Erie especially is vulnerable to these occasional algae blooms that usually hit in the summer. And as you can see here, it can cause this kind of disgusting green pea soup color, and it can kill fish and other wildlife and other animals that are in these biological dead zones. Another form of pollution in addition to nitrogen runoff is acid rain. This is caused usually by coal-fired power plants and by automobile emissions and so on. It's actually gotten better. It was worse about 30 to 40 years ago, but coal-fired power plants, one of the main culprits that release acid rain into the air, have been phased out by wind and solar and mostly natural gas. Most coal-fired power plants that have been retired have been replaced by natural gas, not wind turbines or solar. And because of that, it has gotten a little better. But this is a picture of a forest in southwest Germany that was hit very hard by acid rain. Acid rain has hit places in Canada as well. But the good news is when you cut down on the amount of pollution, forests can recover fairly quickly from acid rain. So the trees that die will eventually die and break down. But if you can cut down on new acid rain sources, they can recover fairly quickly within about 20 years or so. So in addition to air pollution, another environmental problem that's related to soil is soil erosion. If you have an area where you have lots of animals that are eating lots of vegetation, that can pull up the vegetation that anchors down the soil, and that can cause erosion. Areas on the outskirts of deserts are vulnerable to this. It's called desertification, where you have maybe a steppe that's dry, but it has some grass, but then cattle come and eat the grass. Then there's nothing to anchor down the topsoil, and the desert can kind of encroach on what had been a prairie or a scrub area. So this is an example of erosion in Kenya, where crops on a steep terrain have created a gully. So again, they basically weren't wise with the irrigation practices, and now this gully is kind of formed on the outskirts of their farm. This happens in the US too. During the 1930s, there was something called the Dust Bowl, and basically it was caused by drought. And also during the 1920s and up to the 1920s, lots of prairie and natural grass that had anchored down the soil had been turned into farmland, and corn and soybeans were grown. But then starting with the Great Depression, the value of these commodities plummeted. No one could afford to buy them, so farmers stopped planting them. They were losing money growing corn and soybeans and crops. So that left a lot of farms exposed. They had nothing to anchor down the soil. So that, in conjunction with a very bad drought during the 30s, led to lots of topsoil being blown away in these horrible dust storms that hit during the 1930s. And they came back in the 50s and 70s, but they were really worse during the 1930s. Scientists at the time weren't exactly sure why that was happening, but then they realized that you have to keep some kind of cover crop on the soil to prevent it from blowing away if there's a time of drought or high winds. And now there are better farming practices than there used to be in the 30s. These are some pictures of the Dust Bowl. The picture of the woman on the right is a rather famous picture. Her name is Florence Owens. She has 3 of her 7 children in this picture, and this is her in a pea pickers camp in California. She had left Oklahoma, and this is her after she arrived in California. A lot of people from the Central Prairie areas moved to California or other parts of the U.S., which were not suffering from as bad of droughts and so on. But you can see here, based on these pictures, it was really bad, and many small towns were devastated by the Dust Bowl. So ways to help prevent these kinds of things. The World Commission on the Environment has said it's important to have development needs that are present without compromising the ability of future generations to meet their own needs, which is kind of vague, but essentially, try to consume as little land and water as possible, preserve soil for future generations, try to protect forests and wetlands and so on. Also, problems that need to be addressed is the conservation of flora and fauna, plants and animals, and population and poverty. The Earth's population just passed about 8 billion, it's estimated, a few months ago. It's expected to peak around maybe 2070 or 2080 at about 9.5 to 10 billion. It's hard to know. And then some demographers think the population actually might start to flatten or even decline in the early 21st century. Many countries have already had declining or crashing populations, especially South Korea and Japan and elsewhere. But then parts of Africa and Pakistan and other Central Asian and South Asian countries are still growing fairly rapidly. So it's hard to know what the population is going to be beyond about 30 or 40 years, but most scientists think it'll peak around maybe 9.5 to 10 billion and then flatten or start to decline. So there's one kind of famous community in Florida called Babbitt Ranch, a population of 4,600 people. And they were famous a couple of years ago because the whole development is powered by solar panels. 700,000 solar panels create all the energy the development needs, and it powers all their buildings and community centers and schools and so on. As you can see here on the top right, 700,000 power plants is pretty big. That takes up a lot of space. So the power plants and the solar panels are about the same size as all the buildings themselves. And it also has sustained itself very well after the last hurricane. Hurricane Ian hit in 2022. Many communities were really devastated by it, but they managed to survive very well. They didn't lose power. Very few solar panels were damaged. So now this community is being seen as a way of building hurricane-resistant communities as well as green communities. So that sounds great. You might think, why don't we all move there? But here is the local listing of what the homes cost. This 2,900 square foot home, 4 bedrooms, is $1.2 million, a little outside my budget. Here's a smaller one, 2,600 square feet, 4 bedrooms, that's only $1 million. Talon Terrace, that's about 2,300 square feet, about the size of my house, 934,000. So you can see it's a great idea, but this is simply not applicable to regular people. If most Americans can't afford it, you can imagine where if you're in parts of Africa or Afghanistan or Pakistan where they have really rapidly growing populations, this is just not possible. So it's a great way to develop if you have the money, but it's not applicable to a lot of the fast-growing parts of the world that really need sustainable development. So soil formations, this picture here is kind of a cross-section of soil in Minnesota. If you were to go to northern parts of Michigan where they have deciduous forests, it might look similar to that. Soil is a mix of fragmented rocks and minerals and air and some water. And soil is actually considered a renewable resource. It does eventually replenish. It takes some time, but unlike iron ore or oil or natural gas, which is considered non-renewable, soil can over time eventually replenish. So scientists consider it to be a renewable resource. So this is a diagram of soil. It's made up of minerals, organic matter, water, and air. And a lot of soil is water and air. About a quarter of it is water, and about a quarter of it is air. Minerals are about 45%, and organic material, decomposing plants, decomposing animals, is about 5%. So a mineral is a naturally occurring chemical element or compound that possess a crystalline structure, and minerals make up rocks. So rocks are made up of minerals. Common elements in the Earth's crust include silicon, aluminum, iron, calcium, and sodium. Those are the five most common elements in the Earth's crust. The interior of the Earth is made up of nickel and iron, but the Earth's crust is made up of those elements. And again, organic matter is any living matter, plants or animals, that is decomposing and breaking down into the soil. So the upper layer of soil often has a lot more decomposing and decaying matter than is further down. As you get further down, there's less oxygen and less water that get to the deeper layers of soil, so the change in the soil usually slows down. So here are some factors in soil formation. There's the parent material, which is what the soil is originally based off of. You know, you have to start somewhere. So a soil forms by being created or made up of a previous earlier kind of soil. The climate, how hot or cold it is, how rainy it is, the temperature swings, biological agents, those are worms or bacteria, or maybe even animals, like anything that might burrow that can kind of move the soil and move it around. Topography is a key element. That is an area relatively flat, or is it on a hillside? If it's on a hillside, soil facing south will be warmer and probably evolve and change faster than soil that's on the north side. And then time. Given enough time, all soils change. Soils in warmer, wetter environments will change faster because there are more chemical reactions. And then soils up in the tundra that are cold change very slowly. So these are kind of the major factors that create different kinds of soil and change soils over time. So a lot of times people will alter the landscape to better meet their needs. This is a rice terrace in Sri Lanka. You also might see similar rice terraces like this if you were in southern China or Vietnam or elsewhere. And people over generations or centuries have kind of leveled this hill so they have lots of flat steps, which is ideal for growing rice. You kind of need a flat area for growing rice because it sort of creates a pool when you're harvesting the rice. So this is an example of how people, even in pre-industrial times, have managed to change the landscape to fit their needs and change it so they can more effectively grow rice or other crops. Rice fields can be very pretty. Here's a picture of some rice fields here. The two on the left are in Indonesia. I believe the top left one is in Bali, and the two on the right are in Vietnam. Especially the one on the bottom right is really impressive. You can imagine how long it must have taken to have all of those little stepped rice terraces before modern machinery. So biological agents that can break down soil, again, these include bacteria or worms or burrowing animals that break down leaf litter and break down plants and organic matter, and often will turn it into a dark, fertile layer on the top called humus. And that kind of soil is very fertile and very good for farming because it does have organic matter in it. And usually humus is on the top layer of soil. And then as you get further down, there's less humus and there's less air and water as you get further down into the soil. So some soil processes, things that change soil over time, is addition, transformation, depletion, translocation, alluviation, and illuviation with an I. Addition is fairly obvious. That's just anything that lands on top of the soil and breaks down, such as leaves falling from trees. Depletion is dissolved material that's kind of washed down or outside of the area. Transformation is organic matter that gets into the ground and changes and enriches it. And translocation is when you have minerals or moisture coming down into the soil, not necessarily moving away to a different place, but coming down into the soil. So alluviation is a soil process that's associated with depletion, where you have minerals kind of washing down a hill. And illuviation is a process of percolating moisture and minerals coming down into the soil, and that's associated with translocation. So these are different processes that can change soil over time. So you probably read the part on soil profiles and thought, what is this about? But people like to classify climates. They also classify soils, and they often do it by the different horizons or layers that soils have. There are basically three main layers. There's the A, B, and the C layer. Below the C layer is bedrock. That's kind of the hard part of the earth that's not really considered soil. And occasionally, on top of an A layer, there will be a layer of organic or leafy material that is not in all soil profiles, but in some of them. And if that's the case, that's called the O layer for organic. And occasionally, there'll be a transition layer between the A and the B, which is called the E layer, meaning washed out. It's kind of soil that is not quite the A or the B layer. And there are also lots of little subcategories of these broad categories. You can see BT, C1, and so on. And it's kind of like with climates, moisture can change the soil. So people who study soil categorize soil based on these broad categories, A, B, C, and then E and O and R, and also subcategories based on the acidic level of it, based on the moisture, and so on. As you get further down, there's less oxygen and water that gets into the soil, and it changes more slowly. So this is an example of translocation, alluviation, and illuviation. This is kind of a profile of soil that starts out as bedrock on the left here, and then over time, it could be a very long time, depending on how fast the transformation processes are. It can change into a multi-layered soil profile with an A and a C layer. And then as you have moisture and water come down and animals breaking down material, you can have the formation of a B layer. Not all soils have a distinct B layer. And then as time goes on, you can even have a multi-level E layer in others. So usually soil that's been around a while is more complicated with more different kinds of layers in it. The main thing you got to remember is different kinds of soil in different parts of the earth have different layers based on how long it's been there, what the parent material was, the moisture, and so on. So soil regimes, these are kind of the different classifications of types of soil you see. One is aridisol, and as the name implies, arid, these are soil profiles or soil types that are common in desert areas. This is, let's see, light color starts at a depth of about 60 centimeters. That's the BK horizon. So as you go down, there are different layers or horizons of dirt. So one type of soil is the aridisol soil type. And another type are spotosols. This is formed under coniferous forests in cool, wet climates. Michigan might have some kind of these soil regimes. These also have kind of distinct layers. The A layer on the top you can see is dark because it has organic material. Below that is an E layer, the kind of washed out layer. Below that is the B layer, and then below that it gets light again, and that's the C layer that starts at about 80 centimeters or below. So this is an example of a soil regime that you might find in Michigan with organic matter at the top and different layers as you go down. So properties of soil. This particular picture shows soil when it cracks. There's some soil that has a high clay content that might expand when it gets wet and then contract and crack when it gets dry. So this is an example of soil that's cracked and expanded based on the moisture and based on the time of year. So one way scientists can study soil is by looking at a pedon. This is similar to an ice core sample that we talked about a little earlier. Scientists will drill down and get a circular sample of soil, maybe about 6 inches to a foot wide, usually about 4 to 6 feet deep, maybe even further down than that. And then when you look at the cross section of the soil, you can see distinct layers like A, B, and C layers and others. And then based on those, you can kind of classify which category the soil might be in. So we'll talk about the different categories of soil in a second here. So soil texture, soils are made up of different particles of matter, the tiniest being clay and the largest being sand particles. Sand is the coarsest grain. A sand particle is usually 2 to 0.5 millimeters. Silt is a little smaller, that's 0.5 to 0.002 millimeters. And then the smallest is clay, and those are 0.002 millimeters or smaller. One of the reasons why clay is used in pottery is because the clay particles are so tightly packed together, water can't get through, which is why you have pots and things made out of clay, because it's so densely packed together, water can't penetrate it. So this particular chart is kind of interesting. You can see here on The bottom left, if something is 100% sand, it's considered sand. If it's about half sand, half silt, it's considered sandy loam or silt loam. If it's all silt, it's of course classified as silt. And then as you go up between the silt and the clay, you have silty clay loam, and so on. And then roughly in the middle, where you have an even combination of clay, silt, and sand, you have a clay loam or loam. That's kind of well-balanced soil that's made up of equal parts sand, silt, and clay. So to having different kind of textures for soil, soil can come in different structures as well, kind of how it's shaped if you look at it. One way that you have soil is in kind of layers like plates. That's called platy-soil structure. This photograph demonstrates that. So platy soil has a horizon and a plate-like structure, a horizontal plate-like structure. So again, kind of little layers stacked on top of each other like pancakes. That would be a platy soil structure. Others are sort of column-like soil structures called prismatic soil structure. That's a diagram and a photograph of a prismatic soil structure there. They have vertical columns and structure in the B layer. And then additional soil structures are blocky or angular soil structures. This is when you have blocky soils with particles that fit together, kind of like building blocks next into each other. So fairly large and irregular and angular in shape. And then finally, spheroidal soil structures. This is when you have lots of smaller kind of round soil particles that are clumped together. So they're small and nearly round, kind of like breadcrumbs. This is highly porous, so water seeps through it fairly easily. So it's kind of the opposite of clay. So those are kind of the four main kind of soil structures, how soil is structured in the wild. The development of soil, this kind of talks about how soil changes over time. This is looking at a fictional soil profile on the left and shows how it changes as you go to the right. So as you have organic matter coming down and water coming down, that can kind of break up the soil on top. Roots of trees can kind of break up the soil, which let more air and more water down deeper into the ground, which can further break up the soil and cause chemical reactions. And then as that process goes on long enough, often small particles like silt or clay can get in. They can kind of block and prevent water from getting down further in the soil, and then the chemical processes and changes can slow down or stop. So a positive feedback is a process that makes something go on more rapidly. So if ice melts, that means more sunlight starts to hit the ground. The ground is darker, that heats up and more ice melts. That would be an example of a positive feedback loop. And a negative feedback loop is something where it sort of cancels itself out or stabilizes it. So if it's really cold in Asia, the cold weather will often attract moist air from the Pacific during the winter. The moist air will move into the cold, dry parts of Siberia, and that actually negates the cold, dry air. So that would be an example of a negative feedback or something that kind of cancels or stabilizes it. So soils go through both, usually a positive feedback at first, and then over time it can turn into a negative feedback as water and oxygen and decomposing matter no longer can penetrate deep into the soil. So classifications and mapping of soil. This is northern Wisconsin. Again, northern Michigan might look similar. They have soil that is developed under deciduous forest. And this has been clear cut on the left. So they have farmland on the left and then the natural woodsy area on the right. In the upper Midwest, they have soil types called alpha soils that are fairly common. And they're fairly good for farming, although there are other types that are a little better. But it's a common kind of light tan colored soil that you often will see in the upper Midwest. So organizations of soil taxonomy, just like we talked about different climate zones, A, B, C, and so on, and then they have subcategories. Soils have broad categories where they're classified as aerosols, mollisols, alpha sols, altisols, oxasols, spotosols, gelisols, antisols, inceptisols, histosols, vertisols, and andisols. Those also have even more detailed subcategories that you don't have to worry about or think about. We'll just focus on these kind of broad categories here. There are 7 soil categories that are found in specific area and climate types: the aerosols, mollisols, alpha sols, altisols, oxasols, spotosols, and gelisols. The other 5 are found all over the world in small little pockets and not necessarily associated with a specific climate type. So here's an example of some of the subcategories. And again, you don't have to memorize or worry about this, but the soil profile of an antisol, that soil type is broken down into the subcategories, the Arents, lac horizons, so on and so forth, while it's then continuously saturated with water. Alpha sol, same thing. All the soil orders have small subcategories within them. And this is kind of interesting because it kind of shows you where the name came from. Aridisol, Latin for dry, so arid means a desert. Mollisol, Latin, mollis is Latin for soft. This is soil that you'll see often in grasslands, usually rich. And you can see here, you don't have to, we won't go over all of them now, but you can see this kind of helps you remember what the soil is related to if you can remember what the origin of it is. Another one is kind of interesting. The spotosol, spotos is Greek for wood ash, and that's a Russian term. So these spotosols are often in areas where you have coniferous forests. Inceptisol, inception is Latin for beginning. These are soils that are just barely starting to develop a profile, kind of soil in the early stages of forming a specific soil type. So that's where the origins of the words come from. So this is a soil taxonomy. And this is kind of interesting because it shows where you'll see these broad families of soils in different parts of the world. On the bottom is the equator, and as you go up, you move towards the North Pole or South Pole if you were to flip this. And on the left, it's a moist environment, and as you get further right, it gets drier. So near the equator where it's wet, you have oxasols, then altisols, alphasols, and then when you get into dry areas, you have iridisols. As you get to temperate mid-latitude climates like the southern to central part of the US, where you have moisture, you'll have alpha sols. Then where it's drier, you'll have mollisols, where you have grasslands. And then drier still, you have scrub, where you'll have alpha sols and so on. And then spotosols are common in evergreen forests. And then gelisols are common in the tundra, where you have permanent frozen soil or permafrost. So this is kind of an interesting way of seeing where different soils are in the world. So we'll quickly go over the main categories. Aridisols are soil types that you'll see in dry areas. This is a picture taken in the Great Basin of Nevada. The Great Basin and other basins are areas where when rain falls into them, it does not flow out to the ocean. It stays in that area kind of like a bowl. So most rain that hits in western Utah or almost all in Nevada will eventually either evaporate or flow into the Great Salt Lake. So any rain that falls in this area, which isn't much because that's fairly dry, the Great Basin, will stay in that geographic area. It does not flow out to the Pacific Ocean. It's its own watershed. Mollisols are soils that are rich in decomposing matter and found in grasslands like in Nebraska or Kansas. They have dark soil on top because of decomposing grass that's decomposed over centuries. So parts of the US and Asia have this. And it also has a lot of burrowing animals that live in it. I just like prairie dogs and burrow owls. I just wanted to incorporate them into this presentation in some capacity. But these are animals that dig holes and increase the change of soils by adding more air and more water that gets into the soil by kind of churning it and mixing it up. So these are biological agents that speed up the transformation of soils that are found in prairies. Those owls are kind of funny. Most owls are nocturnal and they live in trees. Burrow owls are awake and active during the day, and they live underground in holes that other animals dug. So they're very unusual owls. Alpha sols are soils that are found usually in higher latitudes. Deciduous forests have lots of these, and they often have an A and E horizon to them. So Michigan might have some alpha sols. Altisols are found in the parts of the southeastern part of the United States. They're often very reddish. They have iron and other elements in them that kind of give them the reddish hue. This is soil that was commonly used for growing cotton in the southeast, but it's not particularly rich. It needs to have a lot of fertilizer added to it. So in many southeastern areas, they've stopped growing cotton and they've started planting trees that do a little bit better in the somewhat marginal soil. So they're in warmer, wetter climate zones, and they're often associated with CF climates or continental, mid-latitude mild with continuous rain. So common in the southeast. Oxasols are often found in rainforests. This is also dark red. It's not particularly rich soil. It's soil where almost all the nutrients are sucked up into the plant life above the soil, so the soil itself is fairly devoid of valuable minerals. So it's not really good for farming. People who want to farm in rainforests or savannas often have to burn the forests down. That improves the nutrients temporarily for a year or two, but then it gets washed away or depleted from farming. And then you either have to add artificial fertilizer or move to a different part of the rainforest and continue the process of slashing and burning and farming that area for a few years and then moving on. So if you live in a low density area, this can work, but in areas where you have a high population, it's not very practical. Gelisols are soils, again, in the tundra that have lots of organic matter that is trapped in them, lots of methane is in them. Again, it's usually associated with permafrost. Entosols is soil that's basically difficult to even classify because it's not really formed yet. Entosols contain soils that don't really fit any other category. There's no B layer that's formed, and they're often in dunes or windblown areas or so on. So lots of western Michigan along Lake Michigan might have this kind of entosol soil, which is often dunes and sandy areas. Inceptisols are soils that are just starting to form distinct layers. They're kind of early in the development. They have just the beginning of a B layer. Advanced soils like this often have clay that hasn't built up in large numbers yet. And these are also soils that are kind of scattered about all over the world, not really associated with one specific region. Histosols is soil that has a high organic matter. It often is in swamps or bogs where you have lots of plants kind of slowly decomposing in a damp environment. This picture, the large picture, was actually taken near East Lansing, so that was taken about an hour from here. And histosols are often in boggy areas of Scotland and Ireland. People will actually cut out some of the dark, damp soil, dry out the soil, and then burn the soil as a way of heating their homes in swampy parts of Ireland or Scotland. So there's enough organic matter and methane trapped in the soil, so when you dry it out, you can actually kind of burn it like a log. So the picture there that looks like little slices of fudge or something, that's soil in Ireland that's being dried out so they can use it to heat their homes during the winter. Vertisols is clay-rich soil that is often common in wet, dry savannas and monsoon areas. It expands significantly when it's wet and it contracts significantly when it's dry, so it's not ideal for farming, and it can be difficult to build things on. And then the last one, andesols. This is basically volcanic soil. It's often rich because volcanic ash often is very rich in nutrients. This is in Hawaii. It has an anisole profile of volcanic ash, so it's usually reddish and it's usually quite fertile, although it's a little uncommon because it's associated with volcanoes. But they have quite a few of them in Hawaii. And this is soil profiles of the United States that show the different soils we've talked about and where they're located. You can see some of them are scattered all around. Some of them are concentrated in areas that are fairly specific. The ultisols, the orange ones, are mostly in the southeast. That's kind of the reddish clay. The rich mollisols are in the American prairie. That's the dark green. That's good, rich soil. And then Michigan has a little bit of everything. We have some spotosols. We have some alpha sols and kind of a little bit of everything. So what kind of soil a place has can vary significantly. Some places have a wide variety of soils, especially if they have lots of different elevations and climates. And some are fairly homogeneous, which are overwhelmingly just one type, which is like the prairies with the mollisols and the southeast with the altisols. And here are the different soils on a global scale. Kind of the same idea as the previous map, but kind of worldwide. And as you can see here, the salmon-colored ones are the aerosols. Those are associated with deserts. And then the dark red ones are the oxasols. Those are associated with rainforests. And then lots of different kinds of different soils. And then as you get north, especially in the northern hemisphere, you have the gelisols in the light greenish blue, and those are kind of associated with tundras. So biological processes. This particular picture is vultures eating a dead wildebeest, I believe, in the African savanna. Vultures are actually a very important part of the food chain because they eat decaying and rotting animals that, if they were not eaten, would attract pestilence and disease. So vultures have real strong acid in their stomachs, and they can eat lots of fresh from dead animals, and they can process it in a way that when they're done and they poop it out the other end, it's no longer full of bacteria. It's been purified. So vultures are actually really important for fighting disease by cleaning up dead animals before they can spread disease and attract harmful bacteria and so on. So evolution of life on Earth. Um, this picture on the left here, 5,000 represents millions of years, so that 5,000 means 5 billion years ago. So the origin of the Earth is about 5 to 4 billion years ago. First photosynthesis started about 3.4 billion years ago. And then as you get to about 600 million years ago, you see the area expanded on the right. First invertebrates were about 600 million years ago. First vertebrates about 520. First land plants a little after that. First land vertebrates, first mammals, and so on. There were mammals that overlapped with dinosaurs by tens of millions of years. And then first primates about 70 million years ago, or right before the dinosaurs went extinct. The first hominids, the first kind of primate-like human creatures, were about 7 million years ago. And the first humans, what we would think of as people today, go back about 300,000 years. So this kind of shows the evolution of life on Earth. And for most of it, there were not even invertebrates. The first invertebrate was 600 million years ago. Considering the Earth's about 5 billion years old, that's relatively recent. And humans have been around for about 300,000 of the roughly 5 billion years. So life has evolved rapidly fairly recently when you look at the scale of how old the Earth is. So tropical rainforests are one of the most important biomes or biological reasons because they produce a lot of photosynthesis, which is necessary for the oxygen that we breathe. They absorb carbon dioxide, they release oxygen. And the reason we have more oxygen in our environment today is because of the oxygen created by plants and rainforests, and also algae in the ocean especially. So rainforests are the most productive. They have the most plant and animal life. About half of all life on Earth on land are in rainforests. So they're really considered to be productive, and they have lots of plants and animals and produce a lot of oxygen. Most of the life is in the canopy, high up in the rainforest, not on the rainforest floor, because only about 5% of sunlight hits the floor. So these are some animals in different rainforests. There's a monkey from South America on the top right, a tree frog on the top right, the monkey from South America is on the top left, toucans on the bottom left. In the center is an orangutan from Southeast Asia. Orangutans only live in Southeast Asia. They don't live in South America or Africa. And they're the largest tree-dwelling animal in the world. They're about the size of a person. A large male orangutan can be about 180 to 200 pounds. They're in danger because of habitat loss, but they're interesting animals. And on the bottom right is a person walking on a little ladder that goes through the rainforest. Some countries have tried to preserve their rainforest by turning them into recreational parks with some success. It's a way of preserving the rainforest and coming up with a way of funding it. So very important, lots of life in the canopies of rainforests. So net primary productivity, or NPP, this graphic kind of shows what parts of the Earth are producing the most biomass, the most life. Biomass basically is if you were to take all living things, plants and animals, mostly plants because animals are almost a rounding error, and if you were to dry them out and then weigh them, how much weight would there be? And this is broken down into grams of dry biomass per square meter. So in the green areas, there's 1,500 to 2,000 grams of dried biomass per square meter. And as you get to drier areas, unsurprisingly, like deserts, there's not as much life, not as many plants, not as many animals, and the amount of biomass goes down. So biomass is basically weighing all the plants and animals, how much life is there if you were to weigh it if it was dry. Tropical areas where things grow year-round have more biomass than drier or colder areas. So the food chain and the ecosystem in the food chain, lots of animals, of course, live in different kinds of environments, and animals are either producers. Primary producers are plants that take sunlight and turn them into food that are consumed by herbivores. Herbivores are then later consumed by carnivores, and carnivores can occasionally be eaten by larger carnivores. And every time you have an animal moving from one of these layers to the other. Those are called trophic layers. And plants would be a trophic layer, herbivores would be one, carnivores would be one. I was watching an interesting documentary in Asia. They have Siberian tigers in rural parts of Siberia, and they have black bears there too. And the black bears actually live in nests up in the trees, so they're not attacked and eaten by tigers at night. So while black bears are near the top of the food chain in North America, they're actually food and on the menu in parts of Russia in the east because tigers actually hunt them and eat them. So the documentary showed these huge nests that looked like they might have been built by some massive bird. And in fact, they were built by black bears so they can sleep up in the trees so they're safer at night. So even carnivores can be eaten by other larger carnivores. But when you have an animal, a plant that's eaten by some other animal or animal that's eaten, a lot of the energy is lost. Only about 10% of the energy moves on to a higher trophic layer. So plants take the energy from the sun, the herbivores take the energy from those plants, the carnivores take the energy from those herbivores. And every time you move up a trophic layer, you're losing a lot of the energy, about 90% as you move up. So an ecosystem and food chains, a pond is its own self-contained ecosystem. This particular picture has energy flows and matter cycles through the ecosystem pictured in Britain's Lake Country. And the reason why energy flows and matter cycles is cycle means it's continuously moved throughout a certain area, while energy flows means it comes from far away, but it's not necessarily recycled. Again, energy from the sun does not go back to the sun, so it's not considered a cycle, it's considered a flow. But in this particular um, ecosystem, kind of like the previous picture we saw, sun generates plants and phytoplankton, and small fish eat those, large fish eat those, and then all of the fish and the plants eventually die and decompose, and then those are consumed by decomposing bacteria, or in a forest, maybe fungi that break down that and then put it back into the soil, so it's continuously reused. So like the nitrogen cycle and carbon cycle, ecosystems have food chains where all of the plants and animals are continuously recycled within the ecosystem. Something that's going on now in Michigan is ethereal ponds, also known as vernal ponds. And these are basically ponds that temporarily show up in the spring when there's been heavy rain. And these are very important to the environment because lots of amphibians and other animals will lay their eggs in these ponds because they don't have predators like fish to eat them. So if you lay eggs in a pond where there are fish, it's a pond year round, then a lot of what you lay could be eaten by fish. But since these are temporary ponds that form very briefly in the spring, there aren't any fish in them, and they're very important for breeding salamanders, frogs, or any kind of aquatic animal that would lay their eggs in the water. So these ethereal or vernal ponds are very important, and there are many of them right now in woodsy parts of Michigan. So this talks a little bit about what we spoke about before, the different layers of energy and different layers of the trophic system. Only about 10% of energy produced in the form of food is passed from one trophic level to the next higher level. So plants lose a lot of energy when they're eaten by herbivores. They lose energy when they're eaten by carnivores and so on. It just kind of shows if you want to be really efficient and you want to be good for the environment, maybe one of the best things to do is to just eat vegetables because they require a lot less energy than growing vegetables that you would then feed to animals, and then you'd eat the animals. But I also like steak and chicken, so I'm not going to completely give up on eating animals quite yet. One thing that's kind of interesting and fairly new is growing animals and plants together. It's kind of a symbiotic relationship. This here is an aquaponics station in California where basically they grow lettuce and leafy vegetables on floating tanks of water. And then that water flows into tanks where they raise tilapia, the fish on the upper right. And then the tilapia waste goes back into those tanks, and the plants absorb the tilapia waste like soil. It enriches the water, and then it kind of forms this closed loop where the plants and the animals actually benefit each other. Tilapia are very efficient animals to raise because you can grow a lot in a small amount of space. And because they're cold-blooded animals require a lot less food than warm-blooded animals because they don't have to eat as much food to keep their body at a constant temperature. So if you Want to be really good for the environment, you can eat lots of fish and try to avoid plants or try to eat plants and plants and animals that are vegetarian instead of carnivorous. So plant succession, this kind of shows a lake where you have vegetation kind of form on the edge, and then a lake. First of all, it usually has vegetation forming along the edges of it and then in the middle of it. And as time goes on, the bushes along the side and plants can grow into larger trees. And then eventually, trees can grow and kind of move in and completely overtake the lake itself. So this is, as it says, an idealized sequence of plant succession where a lake eventually colonizes shrubs and trees. So this is a transition from a lake to an area overtaken by trees that might happen in the forest. So this is an example of plant succession. Secondary plant succession is when you have some kind of natural disaster, a forest fire or clear cutting that wipes out a large area, and then you have an abandoned field. And then from there, you'll usually have pines that can grow more quickly, move in first. And then as the pines die off, they can enrich the soil. And then deciduous hardwood forests that grow more slowly, usually move in after the pines do. And then they can take an open field and eventually, usually over 100 to 150 years, grow into something where you have large numbers of deciduous trees. Almost all of Michigan is a secondary forest because so much of it was logged, but there's a small part of Hartwick Pines State Park where they have large natural groves of pines and other trees that were not logged. If you've ever been there, I've been there once a long time ago. It's pretty amazing. They have some very tall trees there, some very wide trees. And on the top right, you can see some pictures from people from the 40s visiting a tree and kind of giving it a big hug to see how large it is at its base. So they have really huge trees in California, redwoods, but they have some fairly large older trees in parts of Michigan as well. So different plants and animals are kind of limited by the zone where they can live. Some are more adaptable than others, but a lot of plants and animals have a narrow range where they need a certain amount of moisture or a certain amount of temperatures for them to survive. And as you get further and further away from their optimal range, it becomes more difficult and stressful for those animals or plants to survive, and they're less likely to make it. Islands often have very unique flora and fauna that are specific to that island. And then you have some plants and animals that are very common and found almost everywhere. So the laws of tolerance kind of limit how certain plants and animals can adapt to different environments, and some are more tolerant and adaptable than others. Some of the more tolerant animals that are adaptable in North America include the cougar on the top right, the black bear, the cougar on the top left, the black bear on the top right, coyotes on the bottom left, and the raccoons. Raccoons and coyotes are actually very adaptable to live in urban environments. Chicago has about 4,000 coyotes that live in the urban area, and they're called Wile E. coyotes because they are so adaptable. So these are animals that can live in hot or cold environments, urban environments, rural ones. And then there are some animals on the opposite side of the spectrum that are specifically designed to live in a unique environment. Pandas on the top left only eat bamboo shoots in eastern bamboo forests of China. On the bottom left is a kiwi. That's a flightless bird that lives in New Zealand. There are no mammals in New Zealand other than bats, so it has no natural predators, which is good because that thing would not last long against a coyote. And then on the right are koala bears. Those are animals in Australia that only eat eucalyptus leaves. They can't eat anything else than that. They eat eucalyptus leaves about 6 or 7 hours a day, and then they nap most of their lives because eucalyptus leaves don't have a lot of nutritional value. So they have to eat a lot and they have to take it easy, or they can't survive. So they're pretty calm animals. They're unique because, as you can see, they have two thumbs. They have two thumbs on one side of their hand and three fingers on the other. So they're pretty cute. I've seen some of them when I was in Australia. And in invasive species, when you have an animal that's not from an area originally, sometimes they can actually adapt and take over fairly quickly. In Australia, rabbits are not on the continent. They were brought in there, and I think for food 150, 200 years ago. Then some escaped. And if you know anything about rabbits, they breed very quickly and they multiply very quickly. So the number of rabbits in Australia can get out of control. They actually have a huge fence along the eastern part of Australia to try to keep the rabbits on one side of that fence. It's called the rabbit-proof fence. It goes for thousands of miles in Australia. and it's been partly successful. But Australian scientists are constantly looking out for any disease that might be killing rabbits, because as soon as they hear one, they find the disease, they bring it back to Australia, and they deliberately release it on the wild rabbit population of Australia to try to keep their numbers down. So they're a big problem. They've taken over much of Australia. A lot of the animals from there are not adept at competing with them, so they're a major problem. Some invasive species in Michigan include sea lamprey on the left here. There are these disgusting worm-like things that have teeth that are originally from the Atlantic Ocean that have moved their way into the Great Lakes. Officially, or earlier, the Niagara Falls acted as a natural barrier that prevented them from getting to the Great Lakes, but because of more canals and more shipping, they've slowly worked their way into the Great Lakes, and they can attack other fish and suck their blood. Usually in the ocean, they're non-lethal, but in Great Lakes fish, they're often lethal, and they can die from having their blood sucked or die from infection, and they can be a real problem. Thankfully, scientists have realized that if you use certain chemicals in areas where they breed in streams before they are fully grown, you can significantly knock down their numbers. So they're not as big of a problem as they were in the 1980s. The top right is the murder hornet or Asian giant hornet. Those are slowly moving their way into Washington state. They're these big, nasty looking hornets. I heard they're not particularly aggressive, but they're massive, and if one bit you, you'd feel that. And on the bottom is the emerald ash borer. Those are originally from Asia. They've gotten to the Midwest and they've wiped out millions of ash trees. The city of Jackson lost hundreds of ash trees in some of our parks. We had to pay some people to cut them down and get rid of them. So these are examples of invasive species in North America. So endangered and endemic species, these green areas are areas that are called biodiversity hotspots, where there's a lot of different kinds of plants and animals unique to that area that are endangered and not particularly adept at competing with invasive species. Madagascar has lots of unique flora and fauna. Central America, the Caribbean, the Caucasus, and a lot of other places on this map have interesting, unique flora and fauna that are unique to that specific region and usually not found elsewhere. So global distribution of plants. This particular picture is kind of a hilly area in East Africa. The area near this forest is mostly open savanna and drier, but on this particular hill, it's cooler because it's higher up and they get moisture from the wind blowing in, so it has a unique microclimate of plants that are very different than the surrounding environment. So global biomes. These biomes are basically large subdivisions of plants and animals that are across the country. They're often closely associated with a specific Köppen climate. Deserts would be BW climates. Temperate grasslands would be tropical wet dry savannas usually. Temperate forests would be usually CF climates. Mediterraneans would be usually CWA or CWB climates. So these are broad categories of plant life that are found in specific areas. Near the equator, you have lots of tropical rainforests. As you get closer to the interior of continents, you have more deciduous forests, coniferous forests, and prairies, and so on. This is what the biome distribution of North America would look like. So you can see here, we have quite a bit of variety here. In the southeast, you have temperate deciduous forests. As you get a little further north, you have a mix of coniferous forests and evergreen forests. And as you get a little further north still, you have northern coniferous forests. So North America has a wide variety of different kinds of plants and animals in the area. As you go up in altitude, it gets cooler, and then you can have a significant change in the environment based on the altitude of a specific mountain. This particular mountain is a diagram of Mount Chimborazo, which is on the equator in Ecuador. And a famous geographer, Alexander von Humboldt, climbed to the top of this mountain and took detailed notes. And he noticed that as he went up in elevation, it was very similar to if he were to go north in latitude. So above a certain line of elevation, there were temperate forests like you'd have at latitudes above 30 degrees. You went further up the mountain, you'd have northern coniferous forests, which are very similar to as you get about 45 degrees latitude. Higher up still, you get to an alpine tundra, similar to the Arctic tundra. And on the very top, it was a snow-capped peak, very similar to polar ice caps in Antarctica and Greenland. So in this mountain, which is right near the equator, you have a wide variety of climates as you went up, very similar to if you were to move up in latitude on the Earth. Here's a picture of Mount Chimborazo. It's 20,702 feet, which is just a tiny bit taller than Mount Denali, the tallest mountain in North America. That's 20,310 feet. So this is the closest place on Earth to space. And the reason is it's a tall mountain right near the equator. The equator is a little wider than the Earth is at the poles. So technically, the top of that mountain is the closest place on Earth you can get to space. This is the distribution of terrestrial biomes. We looked at this before when it was referring to soils, but it also applies to plant life as well. And some of the major biomes, again, are tropical rainforests, which we talked about along equatorial regions, very productive, lots of plants and animal life, rainy all year round. As you go north or south towards the poles away from the tropical regions, you get tropical wet dry savannas. This is when you have a distinct rainy season, but often a much longer, drier season. Monsoons are also similar to this. That's when you have a stronger, heavier wet season, kind of in between tropical savannas and tropical rainforests. As you get further north above 15 degrees to about 30 degrees, you have deserts, desert biomes. They have poor soil and it's drier. Usually deserts have 10 inches of rain or less, but they do have some plants and animals in deserts. This is in Arizona. If you've ever seen cacti, cacti are almost exclusively to the Americas. There are very few of them outside of the Americas. So if you've seen a movie and you don't see cacti in it, they probably filmed it in Italy because in the Southwest there are cacti almost everywhere. Temperate grasslands are these wide open grassy areas, usually in the interior of continents, where there's enough moisture to support grass, but not enough moisture to support forests. So kind of in between deserts and forests. And this is in the Oklahoma's Tall Prairie Grass Reserve. The grass there can grow up to 6 feet tall. This is what much of the American prairie looked like before much of it was plowed and turned into farmland. And temperate deciduous forests are in C or D climates. These are forests where the leaves are dropped during the fall. This is what most of Michigan would be an example of. They usually have significant temperature swings, warm in the summer, cold in the winter. Temperate evergreen forests are a little bit like evergreen forests in northern Canada, but a little warmer. They're often found on the western coasts of temperate climates. The Pacific Northwest would be an example of temperate evergreen biome. They're fairly rare, not real common. Then the Mediterranean scrub biome. This is where you'd have a dry, warm summer and a cool, drizzly winter. Southern part of California will be like this. The Mediterranean, Italy, Athens will be like this. Parts of North Africa, parts of South Africa as well would be like this. It's considered ideal by many people because it's pleasant and warm in the summer, but there's enough moisture to support some kind of plant and animals and cultivation. This picture is of the Amalfi Coast in Italy, which is kind of a resort area. And a lot of the world's largest cities, especially older cities, are in this particular biome. Rome, Athens, Istanbul, some of the world's real large old cities are in this biome because it is such a relatively stable, good climate for raising crops and living. It's not too hot or not too cold. Northern coniferous forests are common in northern Canada and northern Russia. Siberia would be an example of this. Southern hemisphere doesn't have any of these because they don't have land masses large enough to support them. And then north of that is the tundra, and north of the tundra is ice caps where there really isn't any plant life, so it's not considered a biome in the sense that the others are. Tundras have very little plants, lichen, some small shrubs. It's too cold and too dry to support forests, so it looks a lot like this. Relatively little life, but some life. Finally, zoography, spatial aspects of animal population. We kind of talked about the distribution of plants before. Now we'll talk about the distribution of animals. Zebras are herbivores that are in this picture eating some of the grasslands they have in the Serengeti and parts of Africa. Those would be tropical wet dry savannas. Lots of herd animals live in these warm, relatively wet grasslands that they have in Africa and parts of South America. And The book talks about an animal's habitat, a range, habitat, and niche. An animal range is fairly straightforward. It's where you can find the animal. These examples are the range of the black bear, range of the gray fox, range of the squirrel, range of southern flying squirrels, and so on. So the range is where an animal can be found, where an animal is likely to live. Within a range is a habitat. A habitat is a little more specific. It is within that range, where would you likely find an animal? So gray squirrels, for instance, have a large range, but their habitat would be forested areas. And other animals, certain frogs might have a large range, but their habitat would be swampy areas and areas where there's a combination of flooded forests and so on. And then a niche is even more specific still. A niche is the environmental space within an organism operates most effectively, or which it's most effectively adapted for. So that's kind of a subcategory within a habitat. And an example of a niche is the Kirkland's warbler. The brown area is the range of the jack pine that they have to live in. So their habitat would be jack pine, but their niche is very specific areas in northern Michigan, and they winter in the Bahamas. So they actually have a fairly large habitat, which is the pine areas here, but they're most likely to live in these relatively specific niches within northern Michigan or the Bahamas. So it's kind of a, a subcategory within a habitat, which is itself within the category of a range for an animal. So adaptations and processes for evolution. Animals, Charles Darwin and another contemporary named Alfred Russel Wallace both wrote books about natural selection in 1858. They were actually working independently of each other. And then by chance, they wrote a similar thesis on how animals evolved and published them in the same year, 1858. And basically, their idea was that certain animals inherit certain traits from their parents that give them an edge or an advantage. And those animals that have that genetic change or advantage are more likely to pass that on to future generations. So in Africa, giraffes had longer necks because they were more likely to reach taller trees that other animals couldn't get. The giraffes that had longer necks were more likely to get more food, less likely to starve, then they would pass those genetics onto their offspring. And then you'd over time have giraffes that would evolve longer necks, more adapted to the environment. Something that's interesting that's been going on recently is elephants in Africa have been poached so heavily that a small number of male elephants were always born with small tusks or no tusks. But there weren't many of them because the females prefer elephants with larger tusks, so they weren't reproducing. But because so many elephants have been poached for their ivory, the number of male elephants with no tusks or small tusks is actually going up because they're more likely to survive because they're less likely to be shot by poachers. So that's kind of an example of evolution fairly recently in the last 20 or 30 years, where this what was a small number of male elephants with this relatively unusual trait are now becoming more common because they're not being poached, and what was a disadvantage is now becoming an advantage and making an elephant more likely to reproduce, having smaller tusks that makes it less likely to be shot by poachers. So the Earth's zoological realm, they use a bear to kind of demonstrate how a specific kind of animal can evolve in different parts of the world. There are 8 kinds of bear. I thought there were actually a lot more than that, but there aren't. There are only 8. There's the polar bear, brown bear, American black bear, Asian black bear, sloth bear, sun bear, spectacled bear, and giant panda. You're probably familiar with most of them. Asian black bears are similar to American black bears. The sloth bear is actually native to the Indian subcontinent, so they have them in India. The sun bear is the smallest bear species, and they're from Southeast Asia, especially in parts of Cambodia. And the spectacled bear is from South America. So bears are from all over the world, really, found in the Arctic, tropical areas, all over, but different kinds of bears evolve to different kinds of climates. And it's thought that about 7, 8 million years ago, all bears were probably one kind of bear. And as time went on and environments changed, it kind of split into different subcategories and subspecies. And now panda bears are in Southeast China, spectacled bears from South America, and polar bear, brown bear, American black bear, Asian black bear, and other sloth bears probably evolved about 1 million years ago from one kind of bear. And now there are these 8 different species of bears that evolved over time to adapt to their environment. It's thought that polar bears may soon go extinct because so much ice is melting in the Arctic, which is what they need to live on. That's their habitat. And brown bears may actually replace polar bears in the near future. And we may only see them in zoos if the Arctic ice keeps melting. So Wallace is a geographer we talked about a little earlier. He was a contemporary of Charles Darwin, and he looked all over the world and examined different kinds of climates and where different animals lived. And he noticed there was often a stark break between one kind of plants and animal groups and then another. And he thought the animals in Borneo and South Asia were very different than the animals in Australia. Australia had marsupials, they had kangaroos and so on, and none of those animals were found in the parts of Southeast Asia they looked at. And he wrote or drew what was called the Wallace line, where he thought that there was this stark change in plants and animals. That was later revised slightly. Another geographer created the Weber line, which is the same idea but a little more accurate. But it also kind of separates the Earth into different zoological realms, where the South Asian animals are quite different than Australian, and North American are different than South American, and so on. So there's actually an article in This Week on Wallace that is required reading, very interesting. And many of the barriers and categories that he set up are still valid today. This is World Zoo Geographic Realms, the Near Arctic in North America, Neotropics in South America, Paleotropics in Southern Africa, most of Africa, Paleoarctic, Indo-Malaysian or Oriental Australian, and then also New Zealand and Madagascar. Those are so unique, they have their own zoological categories. But basically, these are realms where they have lots of unique flora and fauna to that region. And then when you cross into a different realm, the animals and plants change very, very significantly. Pictured here on the bottom left are ring-tailed lemurs. They are indigenous to Madagascar or endemic to Madagascar. They don't live anywhere else. They're primates like monkeys, but they have fur, which is unusual for primates. On the bottom is a kakapo. That's a flightless bird in New Zealand. Again, New Zealand has no mammals other than bats, which is good because it has a lot of flightless birds that would be wiped out very quickly if predators got there. And on the bottom right is another picture of a kiwi. So again, New Zealand, very unusual flora and fauna, no mammals other than bats, lots of flightless birds. So these are some more animals unique to Australia. Again, this is the koala pictured there, kind of eating eucalyptus leaves. They also have wombats on the bottom right, this large kind of furry things. They look like almost little bears. And in Tasmania, they have Tasmanian devils. Those are only in Tasmania. They're not even found in Australia. And they're kind of scavengers. They go around, they eat a lot of roadkill. But they have really strong jaws. And if you were to encounter one in the wild and they bit you, which they likely wouldn't do, they could break your bones. They have jaws that can break the bones of dead animals that they find in the woods. So these are some examples of marsupials. They're all marsupials that are unique to Australia. Some different geographers noticed that islands tended to have more animals the larger the island was. And some scientists studying islands in the Caribbean, MacArthur and Wilson, actually came up with a chart that showed in pretty accurate detail the larger the island, the larger the number of species found on that island. So a small island like Rendota, which is relatively small, would have very few animals and plants, found about 5 different ones. Saba, which is a little larger, would have more. Montserrat would have more. Puerto Rico and Jamaica, which are the same size, would have about maybe 5,000 different kinds of animals that they found. And then Cuba and Hispaniola, which are larger still, would have more. So it's thought that a larger island would have more variety of climates, more variety of plants and animals that you could survive off of so they could support a larger population. So this is a theory that's been largely proven and seems to make a lot of sense. So just a few more slides, then we're done. Recolonizing an area after there's some destruction. There are times where volcanoes have erupted and they've wiped out almost all the plants and animals in the nearby surrounding area. This particular picture shows an area in Tanzania that was hit by a volcano and a tree just barely starting to sprout up and recover. More famously, in the United States, Mount St. Helens erupted in 1981 and obliterated in coal ash a very large area of several hundred square miles. And scientists have been studying it very carefully to see what would happen and how long it would take to recover. And you see some aerial photos here of before the eruption, and then the vegetation slowly coming back after a few years, and now it's almost fully recovered. And there's a picture of what it looked like in '83, where there was still coal ash everywhere and dead trees everywhere, and then 2014. So it's an example of how life and plants and animals can recover from an area even after a major devastation like a volcano or perhaps clear cutting of logs or something else, if given enough time and if they have vegetation nearby that can kind of move into that territory. And finally, conservation is very important. Recently, many countries have been putting land aside for wild and for tourism and trying to maybe benefit from putting land aside for nature. The first national park in the world was Yellowstone National Park in 1872. So the United States invented the idea of a national park. And then the national park system was created in the early 1900s and more were added. I think the newest national park is Indiana Dunes, which is on the southern part of Lake Michigan. That was declared a national park recently. And I think we have a little over 65 or 68 national parks in the US. But basically, increasingly, people are realizing that it's important to have some land set aside as wild spaces for the good of the environment and for the good of plants and animals and biodiversity. So does anyone have any questions? You can send me a text, or if you have audio, you can let me know now. All right. If there are no questions, or if you think of something that you want, oh yes, Wesley, I see you have your hand raised. Uh, can you send me the question through the public chat, or if you have a microphone, ask it through the audio? Okay, well, did you say something, Wesley?
I sent you a message. Did you see that?
Oh,
I sent it on through the big.
yep, I do see that. Yes, I'll be happy to speak to you about that after class. Yep. Anyone else have any questions? You can send it to me via audio or through chat. All right. Well, thank you for joining us. And let me see here. Wesley, I can speak to you in a moment. I'm going to turn off the recording and then I can either speak to you or you can send me an email if I accidentally cut you off. Okay.
Sounds good.
All right. All right. Thank you for joining me. Have a good extended weekend.
You are currently the only person in this conference.